it takes a DNA template, okay, that's your DNA. And one of the things you should have read in the book is the DNA strand is always read into what we call 5 prime, 3 prime, 5 prime, 3 prime, and the reason why is because it's 2 strands, right? The word 5 prime, 3 prime is just basically our terminology is saying that's the front, this is the back. 5 is the front, that's the start. 3 is the end. 5 is the start, 3 is the end. The reason why it's like this, 2 strand, because they're complementary to each other. If you still don't know what complementary to each other means, is in the strand here, this is an A, this is a T, right? Complementary. If this is a T, or this is an A, right, because it's TAA, so this is a T, T, A, okay? So this strand's going this way, this strand's going that way, right? And they're always complementary to each other. That's the 5 prime, 3 prime. That's really just a start and stop, okay? But when you're reading this, the frame is, remember, if the ribosome is going to make this into a protein, the frame has to be what? ATG, right? It needs to be going this way. Got that? Because if you tell the ribosome to read it this way, AAT, will it make the proper protein?
No.
No, because it doesn't see ATG. It doesn't know where to start. It's going to keep going until it sees an ATG somewhere here if they have, right? And now your protein is wrong. So you got to tell, or you got to clone, you got to make the machinery face in the right direction. ATG, going that way, okay? And I'm going to call it 5 prime, whatever that 5 is. Okay, so that's the important thing. You need directionality. So, hope you got that. So with PCR, it's just programming, right? You have what we call the denaturing, the annealing, the extension. These are temperatures: 94 degrees, 72 degrees, 60 degrees. That's just a process. You should read about that and what's happening. And so what's happening is, when you denature it, you basically open up 2 strands, okay? You open up 2 strands, and again, this is 5 prime, and this is 5 prime, this is 3 prime, and this is 3 prime, right? You open up 2 strands, and this is why amplification works. Because you're gonna make a copy of this, and then you're gonna make a copy of that. And how do you make the copy? You make the copy by starting these things called primers. I talked about this in last class. Primers are just basically sequences that will bind the DNA sequence. Basically, it starts the culture, right? How many ever experienced this? You put a bottle of water in the freezer, maybe for about 25 minutes, depending on your freezer. 25 minutes to 30 minutes. So you look at it, and it's not yet frozen, but it's cold. And then you pick it up, and then all of a sudden it freezes. You ever get that? Yeah. Right? That's called supercooling. You know how that starts? There's a little snowflake in the bottom, a starter culture, that water molecules start to bind, and that's how ice freezes, right? It's a starter culture. You always need that starter culture. So it's great if you pick it up, and then you just tap it. It allows the reaction to go faster. That's what primers do. Primers allow for the reaction to occur, but you need a primer. For those of you who paint buildings, you don't add a primer, the paint's going to peel out, right? You need the primer to bind first. Okay, that's the whole concept. That's what we call a primer. So, we need a primer. We need to start the copying here. And the copying, let's say, okay? So we know this one is A, C, A, G, A, right? You know I got those letters, right? I just copied what's up there, ATG, and then I know this is the complementary strand, right? Got that? So that way if I split it up, it's going to be A, T, G, T, C, T, and the bottom here is going to be T, A, C, A, G, A, right? Are you still with me here? I'm just copying everything that's supposed to be there. And I split the strand here because 94 degrees Celsius, right? I broke the band apart, so they're separated. Now I want to make a copy. That's what PCR is. And what I need to do is make a primer. And the primer is basically, and if you read about primers, and I'll tell you about, a good primer is about 18 to 20 bases long. Okay, 18 to 20 bases long. So that means I'm gonna look here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 to 20 bases long. I'm gonna take that as my primer. So I'm just gonna copy whatever that is, right? Copy whatever that is, and I'm going to use that as my primer. So when you're looking at this, and again, this is where the confusing part might be, right? When you're looking at this, you need the binding of your primer to be complementary, right? So what's the complementary strand of this?
A T.
Right? And so forth, right? And the one here would be actually
A G A C A T. No.
right? That's a complementary strand. See what I'm saying? So you need to bind it, but here's the thing. And I'm just showing you how to make complementary strands right now. It's just opposite, right? Same thing as there. But here's the thing with making primers. I gave you the qualifying. Primers need to be what? How many long?
18.
About 18 to 20. We call it 18 to 20 mers, 18 to 20 bases. And the way you get that, and I'm going to go away from here. The way you get that is you want to get it from, because you want to make a copy of what? This entire sequence. Get it? You want to make a copy of this entire sequence. And this entire sequence is what? From here to here. So you want to be able to, and you want to imagine this whole sequence is long and it splits apart, and you want to create the primer that is matching this.